All right, welcome back. Let's talk plans for the end of the semester. It's November 12th. We've made it this far. Um, so as you know, there's actually 4 weeks left of class, including this one, next one, and then two after Thanksgiving. And I thought I'd make a little bit of a plan. Of course, we may deviate from this depending on how long it takes to get through stuff. But I wanted to give you a heads up on this. I will be sending this out as an announcement later as well, too. But this week, we're going to talk about multidimensional psychometric models or multidimensional latent variable models. Excuse me, and model fit. Those are the two lectures that are coming up next. Today is multidimensional. Model fit comes next. And then next week, a couple things of note. There will be a new homework assigned. It's homework 5. It's going to be due December 6th. It is a multidimensional psychometric model. So things this week you should be able to use moving forward. There will be a formative assessment that's out. I forgot to actually administer it last week. It's my bad. Sorry about that. Thought I had pushed play on that, but I didn't. So you didn't get a formative assessment. Sorry, Vladimir. No time to talk about it now. But that a formative assessment will be due next week, and then we'll have our final formative assessment due the week after Thanksgiving. Um, Next week we're going to cover model fit and missing data. We'll cover model fit that are supposed to start this week. We'll also talk about empirical priors and scale identification. Both of those are sort of topics that get lumped together. So usually they're two separate lectures, but I tend to teach them at the same day. So then Thanksgiving break or fall break happens. Hooray! We get a week off at the end of November. Everybody happy about that? No class, I promise. Um, but after you get back, we'll have open class times in that week after Thanksgiving. You can work on homework. You can come work on. You can work online. You can basically treat them as office hours if you want. We could talk Bayes, have Bayes questions, get Bayes answers. You want me to do something on the fly that helps your project? I'd be happy to do that as well too. Some of you are doing like multi-level versions of models. I'm happy to help with that. Um, but I always found that teaching in the week after fall break is really difficult. Nobody really cares to pay attention, and they're everybody getting ready for finals. And so this is my way of handling it this year. Uh, Homework 5 will be due at the end of that week, and then big picture, the final week we have project. I would like to put the project presentations. The syllabus says that would be finals week that would happen, but finals week gets a little weird because people leave and whatnot. So I thought I'd put presentations on the last 2 days of class. So presentation, and by the way, I guess the last day, the 13th, according to the syllabus, is when your project is due. So project presentation is what I'm looking for with that, and the motivation for it is I found last time I taught this class and had projects, students really liked hearing what everybody else was doing for their analyses and how they coded it in Stan. So the presentation is basically going to be that. Here's my model, here's some Stan code, here's what I found. Very simple, 10 minutes, 10-minute presentation each. Nothing that has to be super extravagant. You could have even, they don't even have to have a full set of slides. You could have a mark out down document that has, here's my equation, here's my stand code, yada, yada, yada. Cool? All right. Any questions for me on any of this plan? Pause. Today is hot tea day. Cheers. No questions. Okay. We're all good then? All right. Two other things of note. Number one, in your graded homework 3, in your project, I tried to put some comments. I'm happy to help you with any part of the project. In fact, I look at the project as something where I am able to help you build stand code, try to transfer what I'm teaching in class into your own data. That's a valuable skill because class will end very soon and the canned examples will go away. Your data are very different than, you know, what I show in class. Um, so I look forward to, I encourage you to come to office hours or reach out to me to talk about your project. We can even talk over email if you'd like. I'm happy to help you form a model, form a question. Some of you may need some help rephrasing some of your questions and be a little bit more direct or something along those lines, but I'm happy to help with that. Please reach out to me if you need it. Okay. Uh, Number 2, homework 4, which is due this Friday. At the very end of it, somehow I got folders mixed up in my repo. and posted the previous version of homework or some weird combination of the like an intermediate document I had created with the previous version of homework. And you can almost tell this because when I looked onto Icon, I saw 2022 on the file. I'm like, gosh darn it. So I apologize to you for that. The gist of the homework is the same. The model is the same. There's some questions at the end referring to different sections. Those have been eliminated or rephrased, and I apologize for my mistake on that. I actually had the file. I just screwed up which one I loaded, and I feel regretful about that. So, anyway, whenever I say to you, you need more attention to detail, I want you to turn around and show the mirror to me. Okay? Okay. Very quiet today. Other thoughts, questions? Anything you have questions about last time? Yeah, Vladimir. Yeah. Interesting. Good. Good, good, good. Okay. Well, let's see what I can do here. All right. Let's get into the lecture. So yes, Vladimir, let me look at actually, sorry, the freak out happened while we were talking about homework. Let me get to the homework real quick. I'm really sorry if I screwed that up. Yes. Yeah, question 6 should not be on there either. Sorry. Yes, I changed all of the values. I changed all of the lectures around. Oh, gosh, I can't keep my stuff straight. Sorry about that. All right, I'll get that fixed. We'll get that in there. No question 6. Questions are reduced. The model still be run. Hopefully that helps. Sorry, everybody. Okay, next. Thoughts, questions, comments about what we did before. Try to calm down. I feel very uptight now. That mouse thing really threw me off. No comments or questions. All right, here we go then. Let's do this. Generalized measurement models. Modeling, we're going to talk about modeling multidimensional latent variables now. So in scaffolding this class, what I tried to do was to build um, uh, sort of one thing at a time we change, right? And so we started with CFA models at the unidimensional, right? We used normal distributions, and then we kept the unidimensional latent variables, but we changed to categorical distributions or to um, after categorical distributions, we had categorical distribution. We had binomial, we had multinomial, et cetera, et cetera. So I'm still like hung up on my mouse. When tech breaks, it's one of my weaknesses. I just get all enraged and I can't pull myself together. I got to find it, pull it through here. Okay, so the things that changed there were the item side, right? Now, this time, what we're going to change is the theory side. Instead of having one trait we're measuring, we're going to have multiple. And I'm going to warn you right now, this is a little bit more difficult, particularly because of how we structure the multiple latent variables together. We're going to have to use a multivariate normal or a multivariate distribution for the latent variables, and that causes a few hiccups. Additionally, we use confirmatory models for what we do, right? There's no exploratory version of there's no exploratory factor analysis when it comes to likelihood based estimation. You have to make constraints to identify your model regardless. And so all of what we're doing is just the constraints based on model the Q matrix that we described before. So let's dive in. We're going to use the polytomous data model, so the graded response model that we saw before at last week. And we're going to take it and estimate two latent variables in the context of STAN. We're still using our conspiracy theory data. Once again, these data were 5-point Likert scales, and the graded response model models each one of those categories in an ordered sense, meaning 1 is less than 2, 2 is less than 3, and so forth. Cool? We good on all that? Excellent. All right. So let's dive into latent variables. Um, we identify or we build latent variables by specification. I'm drilling this point home, but it's really kind of a key one. Whenever you write a survey, you need to know what you're measuring, right? Sort of one of the philosophical issues I have with exploratory factor analysis is um, the idea that you would create a bunch of items with a known structure and then go and see what an algorithm would tell you how they're related to each other, right? Um, it's not your data's job to tell you what they measure, is something Lisa Hoffman says the whole time. But beyond that, methodologically, exploratory factor analysis algorithms are difficult to work with to almost impossible, and some of the results you get could be spurious. So everything we're doing in this class is purposeful measurement, right? So we define latent variables and then we build items to measure those latent variables. And for us, our definition is always those latent variables follow a normal distribution. So we're thinking of some type of continuum, and then we have to think about how we figure out the mean and standard deviation. This is this. Remember the analysis steps I showed you before. The mean and standard deviation in this case, the mean is we often fix to zero, and we're going to keep that here. The mean for each latent variable will be zero today. Next week we'll change that. And the standard deviation today for each latent variable will be one. So standardized latent variables. Again, we're going to change that next week when we get into um, sort of marker items, the idea where we can estimate the structural model parameters. There are, however, when you have more than one latent variable, there is more than just a mean and standard deviation, particularly if you're using a multivariate normal distribution, in that you may fix the mean to zero, you may fix the standard deviation to one, but you still have to estimate the latent variable correlation. So every pair of latent variables has a correlation, and we have to estimate that correlation matrix. And the history of Bayesian statistics being applied to psychometrics, that one little step has caused more problems, like for years, than we've had that we have in pretty much anything else we've done. Uh, you all, I promise, are really lucky to be in this class at this time. Sorry, my wrist brace is a little warm. The reason why is that prior to I'm going to show you today, back when I started in Bayes, we had no easy way of modeling a correlation matrix. We could model covariance matrices pretty well because there's some conjugate priors that we can use for covariances, something called an inverse Wishart distribution. Um, but there was no way to go and fix a correlation matrix because the correlation matrix is a covariance matrix where the diagonal values are one. So we have to put these constraints on the diagonal. We also have to have the matrix be positive definite, which means we can invert it. These are problems. These were huge problems in Bayesian. And you could see like the literature of the 19 or the 20, the aughts. We call that early 2000s, the aughts. Is that what we say? The aughts, God, I feel old. Because the aughts to me when I was a kid were like 1910s. That's 1900s. Teddy Roosevelt. Anyway, the aughts had a series where all sorts of um, inelegant solutions to estimating this would be. For me, me and a friend, Bob Henson, built something we called a moving window prior. It was like a uniform prior, but if it got up against the boundary, the width of the uniform would change and it would move. Plus, we figured out a way to draw every correlation element from such that it was identified as a positive definite matrix. That took a lot of work. Today's a lot better. We're going to see that. It's still going to be complicated, but that's it. So we create latent variables by specifying which items measure which latent variables in analysis. Sometimes we call that alignment, right? We talked about that a little bit before, the idea that items align to each trait we're trying to measure. In educational measurement, that's what that's called. In fact, if you look at state assessment programs, these are the accountability assessments. Used to be No Child Left Behind. Now it's Every Student Succeeds Act. They almost all of them have to go through this process of peer review, and as part of that, they have an alignment study. Basically, are their items aligned to what they're trying to measure? Um, if you were a factor analysis, you would probably call this a factor pattern matrix. And then in the field I'm most familiar with, which is diagnostic models, the term we called this is a Q matrix, right? Each of these is indicating some way of saying this item measures this latent variable, right? Q matrix, the Q stands for question. This was, to me, prominently used in the 1983 paper by the Tatsuokas, Maurice and Kikumi about, I believe, buggy, if I'm not mistaken. I've heard other people talk about this matrix going back to the 1960s. I haven't read those articles yet either. But I've noticed if you get into the Merck package in R, you can use a Q matrix for multidimensional IRT as well too, and it's called a Q matrix there. So I'm cool with calling it a Q matrix. Sound good? The idea that we call it question matrix, that term question, I feel like these are all sort of statements and prompts, whereas questions I feel like are more educational measurement based too, which makes more sense. But anyway, okay, how are we doing so far? Questions on any of this? So what the Q matrix or factor pattern matrix holds is an alignment, right? Basically, the idea is the alignment provides a specification of which latent variables are measured by which items. And that's how I like to refer to it as, right? Um, if you think there's a tendency to believe in governmental conspiracies, which is, I think, what we talked about a little bit before, um, an item that talks about the government would measure that, right? And it would, so sometimes we say that items load onto factors, but I prefer, I like the term measure, right? The item measures the factor itself. I like that term because it reinforces we're trying to measure this thing that we don't have, right? Items are like our rulers or our measures. A mathematical definition of either of these terms is simply whether or not a latent variable appears as a predictor for the item, right? So remember, in our generalized modeling approach, this side, the left side's the data, and again, this is the weird part, a function of the mean of the data conditional on the latent variable. Once again, in factor analysis, it was just y, because that was its mean, and an identity link, but this could be like a binary response function, like an inverse logit or a logit, and so forth. But on the right-hand side is the latent variable. So here, if we want the non-governmental latent variable to appear on the right-hand side of an equation for an item, our Q matrix for that item needs to have a 1 there for non-governmental and a 0 for governmental, right? So the Q matrix has, for each item, it has an entry for each factor. And here's an example of the Q matrix. Let me grab this real quick. Our Q matrix right here. So we had 10 items previously, and this was, I believe we talked about in in previous classes that our alignment was this government versus non-government. We're going to measure a government conspiracy latent variable. We're going to measure a non-governmental conspiracy latent variable. And each item, whether or not it talked about the government, had a 1 if it didn't talk about the government, and a 0 if it talked about the government. That's our alignment. Sound good? If you want to check whether you like this alignment, by the way, you can go back here to the questions. Um, so, you know, these questions, the first one, even though it talks about U.S. invasion of Iraq, it's more about oil companies and other picked on uh, religions of folks. This first item you'll see is non-governmental for that sense. And you can, by the way, disagree about the alignment. Turns out that's the next class. If you disagree the alignment, what do you check? You check the model fit. You put the Q matrix together, you estimate the model. If the model doesn't fit, problems, right? How are we doing on Q matrix so far? Another thing about the Q matrix. For each of our items, they're either government or non-governmental. So for every model that we have, for every item model, there'll only be one latent variable on the right-hand side. However, it's possible that we have an item that's both governmental and non-governmental. Actually, for these two factors, that doesn't seem possible. Government and government prime seem like complements, right? Logically. So, but in a general sense, it's possible to have an item that measures more than one trait. When you have an item that measures more than one trait, what happens is now on the right-hand side, you have more than one latent variable there. And this is the psychometric part of this class that I want to talk about. How many of you have ever been told a good item measures only one thing? Ever heard that in psychometrics? Maybe. But let me tell you this. How you define your Q matrix may define that, right? So our Q matrix here talking about governmental versus non-governmental, very high level stuff. Let's think of a different context, right? Think of an element. My son's in fourth grade. Let's think of a math test for fourth graders. Sound good? I think all of you have been in primary school before for fourth grade, right? Everybody's been there. Um, if you take the state assessment, the accountability assessment, you usually get a score called math. What's the Q matrix in that sense? It's a really dumb matrix. It's a Q vector, right? There's one latent variable. It's called math, and it's being measured by every item. So every item has a one. It's a one long column of ones, right? Okay, that's what you want. That's what you've been told. That's great. However, when you start taking math as a big concept, which is what we would call a coarse grain size, right? And we boil it down to what's being taught, what my son's learning right now is subtracting fractions, right? And yes, every subtracting fraction problem is a math problem, but the math score that includes other different types of problems, maybe not, maybe for subtracting fractions, maybe displaying data, who knows what it is in fourth grade, doesn't tell him whether or not he can subtract fractions well. So you may have a need to make a definition of a latent variable that's a little bit more narrow focused, right? Instead of talking about all of fourth grade math, maybe we want to talk about his ability to subtract fractions where he has to find a common denominator or convert from a whole number, right? And so what I'm arguing here is the thing that you were told that a good item is an item that measures only one thing. That's pretty good advice. But as you get more narrowly focused in your psychometric model, it's not always possible to create an item that measures more than one thing. Less than one, only one thing, excuse me. In fact, it may be desirable if you're talking about trying to diagnose where he's having problems with fractions. I mentioned he had pneumonia. I think I mentioned he had pneumonia a couple of weeks ago. He missed a week of school, goes back to school, and he's like, Dad, I'm having a hard time with the fractions, like subtracting fractions, right? So I'm like, all right, let's talk about it. So we're talking about it over dinner. He's doing fine, whatnot. But for me to help him, I had to figure out what parts of the fraction algorithms or what parts of the conception of math he's struggling with, right? The idea of what's a whole number, what's our referent unit for a whole number. These are things that he probably wouldn't talk about. But rather than just teach him an algorithm, I know mathematics these days tries to teach concepts. And so I was trying to find that concept. I needed more than just a math score. I needed scores for each of these. So my whole career, I've been studying methods for trying to get multiple scores from a test. And I will say that when you have one item, when you have a latent variable that measures that's measured by one item, or an item that's measured by one latent variable, pardon me, right here. When you have an item like this, that's great. That latent variable basically is driving the entire score process where you're hypothesizing. That's fine. It gets all the information from the item as well too. So there is a mathematical benefit to having one item per or one latent variable per item, but from a practical consideration, you may need more than one, and that's fine. That's fine. Having both on there now becomes a multiple regression. And we could probably interpret multiple regression the same way we would in a multiple regression class, right? The factored loading is now the increase in the expected response, a function of the expected response for every 1 unit increase of theta, holding the other theta constant, right? That's how we would envision it. So Q matrix allows this to happen. Um, that's my soapbox. It's been my focus of my career. Questions on any of this stuff that I just described? No questions. Crystal clear. You can, yeah, Ryan. Yeah, I love the question. Do we still have ones and zeros if we have more than one loading? Yes, ones and zeros have drive the process. Um, there are some really nuanced models, I'll put it that way, nuanced models where folks have developed a Q matrix. So, for instance, do you remember the nominal response model from last week, where each item's options, one, two, three, four, five, um, were sort of estimated separately with different submodels. There have been people who developed Q matrices for nominal response multiple choice questions, right? So where you may have distractors, like in a cognitive test, and they may go to the level of the distractor to create a Q matrix. And then in another nuanced sense, in diagnostic modeling, one of my good friends from grad school's dissertation was making a Q matrix that sort of had more than a number one there to sort of indicate like a categorical level of the factor itself. So you'll see occasionally Q matrices that don't look like this, but by and large, this Q matrix is pretty standard. And moreover, not only pretty standard, it's almost directly a direct representation of what we used to call a factor pattern matrix in factor analysis, which was basically what is our pattern supposed to be of the measurement model. Does that answer your question? That's it. That's it. And in the interest of too much information, because that's what I'm trying to do here. I'm trying to like give you my mind. Um, the other thing I'll note is when you have more than one factor on an item. I don't have one here. Like when you have, let's say this item had latent variable two as well. If you remember linear regression, this is just simple main effects that we have. You may want a latent variable interaction on the item. And latent variable interactions are pretty cool, pretty crazy, and pretty hard to estimate. And I say cool because the field I'm most known for, diagnostic models, their first models were all latent variable interactions. Whereas in CFA world, estimating latent variable interactions on an item was almost impossible up until recently. And so the Q matrix does not imply a latent variable interaction, although it could. You could have columns of products of latent variables as well too. So Q matrix is in this case like a design matrix for your factors. Okay, how are we doing? Okay. The term design matrix I just said there comes from linear models. And you remember the model dot matrix that we had back in the section where we did the linear regression, right? You had to pull that model matrix. That's basically what the Q matrix is going into Stan. All right. So again, you see all these. The same thing happens here. Now, our one thing I will note is in the models that are multidimensional, now we need additional subscripts on our factor loadings, right? Lambda 1, 1 represents this is the factor loading for item 1, that's the first subscript right here, onto factor 1, right? So theta is our latent variable again. And again, it now has two subscripts. Before we just had one theta, so it just had a person. But now it's person P's first latent variable right there. So now we have a little bit more subscripts in our notation. How are we doing? So, okay. Yeah. All right. Buckle up. It's about to get intense. Who likes, who's heard of the word Cholesky before? Yeah, there we go. We're going to Cholesky today. If you haven't, your life will be changed forever. But here we go. Let's talk about what the Q matrix is doing, right? Hypothetically, this would be the equation for an item where we have a Q matrix, right? If we're measuring two factors, like for the first item, hypothetically, that Q matrix element is either a zero or one, right? So if it's a one multiplies the loading times the latent trait, it appears on the item's linear predictor. No, I did not want the dictionary to pop up. However, see, I'm letting it rattle me. I gotta be strong, get through this. You saw before Q1, 2 from this example was zero. So if it's zero, it doesn't show up on the linear predictor itself. So let's think about how we can incorporate a Q matrix into our model equation. We actually can, right? If we set up a vector lambda for item 1 that contains the possible factor loadings, right? This is not things we're estimating. These are things that are possible, knowing that we're measuring two latent traits. We know that it's possible to estimate two lambdas up to some model identification constraint. But let's just hypothetically say it's possible, right? So therefore, we have two thetas, and we put those into a row vector. We put our lambdas into a column vector. then this product, theta times the diagonal matrix of the Q matrix elements times lambda, will result in our item model. Right? So here, this example right here, we had the diagonal of Q is Q, the vector Q, times the diagonal matrix of ones, which turns out to be, and now I notice that on the previous slide I had theta, the first theta here, it should be the second. For the first item in our alignment, this first item in the Q matrix only measures factor 2. So on this slide, it's correct. Sorry about the previous slide. This is a vector of the diagonal of this diag Q results in this matrix right here, where there's only a 1 on the diagonal where the second factor would be. All right, so if we put all that together, we get the following. Theta times this term, this Q matrix diagonal matrix, diag Q times lambda. All right, so let's take the last two together. Again, you don't need to know matrix multiplication, you just need to trust me. But if you know matrix multiplication, you'll know that to do a matrix multiplication, we take the row of the pre-multiplying matrix, multiply element of the post-multiplying matrix, and sum them together. All right, so this first element, this is a 2 by 2 pre-multiplying matrix times a 2 row by 1 column post-multiplying matrix. It will result in a 2 by 1 vector afterwards, right? The first element is 0 times lambda 1, 1 plus 0 times lambda 1, 2, giving a 0 for that first element. The second element is the second row times element-wise multiplication and sum, otherwise called a dot product. 0 times lambda 1, 1 plus 1 times lambda 1, 2 gives you that lambda 1, 2. And then if you multiply this vector by the vector of thetas, you end up with just lambda 1, 2, theta 1, 2. So the Q matrix helps eliminate entries that we need to estimate. And that's important because Stan's item model, if we didn't have a Q matrix, can you imagine coding in Stan? Each line would have to be a different item, and then you'd have to specify the loadings on each line that we had before. So the coding with the Q matrix is important. And because I'm trying to be a nice guy, the emphasis on trying, I created Stan code that uses the Q matrix that you should be able to use for most of what you build. Cool? So you just have to use a Q matrix now in your Stan code, or my Stan code. Borrow it, make it your own. How are we doing? Without that Q matrix, again, what you would have to do in a multidimensional measurement model is for each item, literally hard code the loadings and the factors on each of the means for each item. With the Q matrix, it'll be done automatically, which is nice. Okay. All right. There's our Q matrix. I already showed that to you. This is the item model that it implies, right? So you note item 1 measures only the second factor, the non-governmental factor. Item 2 measures the governmental factor, right? So you can see everywhere where you see a 2 for the second subscript of lambda, that is an item that's measuring the non-governmental factor. Everywhere you see a 1, that's an item measuring the governmental factor. Cool? What else needs to be said? Any questions? I don't know that what else needs to be said. I will say this presentation of Q matrix is difficult, right? Especially if you're not familiar with matrices. But try to work through it a little bit if you can. Now here's where all heck, Bruce. This is where the train runs off the track. What's a metaphor you want to use here? This is where things get more complicated. Okay, so the item model we know is the ordered logistic because we want to use the graded response model, and we saw that last week. But for the factors, we have to change our distribution. Because we have more than one factor, we need to use a multivariate normal distribution. And the reason why we need to use a multivariate normal distribution is because of this thing right here. This is the covariance matrix of our latent traits. The covariance matrix of our latent traits, we have to estimate the off-diagonal elements, right? The factor covariances or the factor correlations, depending on how we've identified the model. If we don't estimate, if we just use a series of standard normal univariate distributions, we are basically saying that our factors are uncorrelated. it is highly unlikely that you have uncorrelated factors when you have more than one dimension. In fact, what you're going to see today, a little bit of foreshadowing, is the government and non-government conspiracy theory is likely to not be two factors. They're very highly related. And the way we know that is through this correlation matrix right here, this covariance matrix. So I'm going to unpack this a little bit. I don't want to just throw notation. Like someone once said, it's like I remember being a student and thinking like stat professors were just like vomiting notation on the screen, and it was like, oh, this mess of like symbols, and I use that word on purpose because it brings an emotion of disgust, and that's what I feel like with equations. So let's try to unpack it a little bit, okay? Um, the univariate normal distribution, this is the generalization. And this is where I'm going to get into trouble, but I'm going to try anyway. Where did you go, Safari? There you are. Okay. I got to go to my favorite Wikipedia. I wanted to grab the univariate normal distribution in Wikipedia and compare and contrast with multivariate normal. All right, we see the PDF of univariate normal here, right? That thing, turns out what we have on my screen, on my slides over here, is a generalization of the univariate normal. And let's describe how. You see the 2 pi under the square root in the normalizing constant? That's our 2 pi right there. If we had one dimension, d, on our multivariate normal, here on my slides, would be 1, right? So with d of 1, that's the square root of 2 pi. That's the same number, right? Then sigma squared shows up in the square root term previously, but in its place, remember, sigma squared is one distribution's variance. We have more than one dimension. So each dimension of our multivariate normal will have a variance to it. And that covariance matrix describes along the diagonal the variance of each dimension and how correlated those dimensions are on the off diagonal. So the analogous term that goes into our distribution now, instead of sigma squared under the square root sign, is something called the determinant of the covariance matrix. Determinant is defined as DET. Determinants are interesting matrix numbers. I'll talk a little bit more about those in just a moment, but you'll note this is raised to the negative 1/2 power, which is exactly what we had down here, right? If we took sigma squared down here is sigma raised to the negative 1/2 power as well, underneath the radical. So let's talk a little bit more about what a determinant is, right? So if we have a square and symmetric sigma, remember that? Two terms. What's a square mean? It means the same number of rows and columns, like a correlation matrix. Right? Symmetric means apart from the diagonal, the numbers above the diagonal are reflected below. Again, like a correlation matrix, right? If the elements of the correlation matrix represent the correlation, then the correlation between variable 1 and with variable 2 is equal to the correlation of variable 2 with variable 1. Right? So the numbers above the diagonal sort of are reflected on below. The determinant characterizes whether or not we can um, invert the matrix. And a matrix inverse is like an inverse in a number. Right? A matrix inverse, think of it this way. We used to call the inverse of 2 1 over 2, or 2 to the negative 1 power, right? And the inverse of a number in non-matrix terms is like if you're saying that number times its inverse equals the number 1, right? So 2 times 2 to the negative 1 power equals 1, or 2 divided by 2 is 1. Same thing happens in matrices. The inverse of a matrix, which is denoted here, if we were to multiply sigma times this negative sigma negative 1, we should result in a matrix that's the diagonal numbers of 1 and 0 is off diagonal. That's our matrix 1 matrix, a matrix inverse. So a determinant is a process by which we can tell whether or not this matrix can be inverted. And we clearly have to invert it because the inverse matrix shows up later in the equation. So our determinant, if it is positive, means we can invert the matrix. And if it is negative, it means we cannot invert the matrix. And if it's 0, um, can't really invert it, but it's pretty close. Like it's like within tolerance, right? It just starts to get to be a mess. So matrices that have determinants that are positive are called positive definite matrices. And if you want to know why, I have no idea. But they're definitely positive when it comes to the determinant. That's my joke for you. Positive definite, positive determinant, right? If a matrix, if you were to say any determinant that's zero or above, so zero and positive, that matrix is called positive semi-definite. And I know that's a trivial distinction to think that determinant, when it's exactly zero, makes the matrix positive semi-definite. But that is a distinction we have to note because in a multivariate normal distribution, the covariance matrix must be positive semi-definite, preferably positive definite. Okay? Now, if the determinant is negative, you can guess what that means. It's uh, non-positive definite. Just because we like, rather than negative definite, which doesn't sound like anything, non-positive definite is what we say. And it turns out normal methods of estimating an inverse are not possible. You have to go to something called a generalized inverse. Those things are weird, and I'm not going to get into those. And Stan, I don't think, has them anyway. So we need, this is the thing that's making our life miserable. Adding one more latent trait means we need this covariance matrix. And when we need that covariance matrix, we got to turn to this multivariate normal distribution. And this covariance matrix makes life tricky. I know you're like, come on, Jonathan, you're making a big deal of this. You don't know how many days of my life has been spent trying to get a covariance matrix to estimate in Bayesian software. Usually software I was writing. All right? So much better now. Questions on any of this so far? No. Okay. Finally, the last part of the normal distribution, if you compare our univariate normal, we have an E here. That's the EXP part. You'll see there's a negative one half here. Well, it turns out that's the negative over the two here. That's the negative one half in the univariate. And in the exponent, previously we had the dimension value x minus its mean squared. Here we've got the vector of each of the thetas minus the mean of theta transpose times our inverse covariance matrix times that same vector theta minus mu not transposed. And what ends up happening when you're multiplying a transpose this, so theta is a vector, mu is a vector, right? So when you do this matrix product or this matrix subtraction and you transpose it, now you get, let's see, theta is a 2 by 1, mu is a 2 by 1. So you get a 1 by 2 matrix here. And then this, if you don't transpose this, you get a 2 by 1 matrix. And so it turns out something transposed times itself in matrix land is the matrix version of a squared term, right? When you see a pre-multiple transpose times the post-multiple, it's like squaring the terms. How are we doing with that? Does that make sense? Okay. And then in the middle, sigma inverse appears, and that's the matrix version of dividing by sigma. Now, it's not exactly that. It's sort of, you have to sort of twist your logic, right? And then matrices, pre-multiplication and post-multiplication matters, but this works. Okay, that's the multivariate normal. Any questions on it? That's what we got to use. All right. Alternatively, the way that we'd specify this in notation, if we're writing about this in like a quant methods type style journal, we'd say the vector theta follows a normal distribution, but sometimes we denote a multivariate normal with a number of dimensions as a subscript. Not always, but sometimes. And then our mean vector for theta means and our covariance matrix for sigma show up as its elements. So this thing looks like a prior for theta, doesn't it? And if that's a prior, that makes the elements of mu hyperparameters and the elements of sigma hyperparameters. So far, so good. And here is the kicker, though. But because we didn't observe theta, we can't always estimate mu and sigma. Womp womp. So we have to do something to them. Womp womp. That's exactly right. I said that in a graduate course. Let's fix that. That womp womp usually means, hey, I can write a paper about that. That's my distinction. Giving out grad school advice here. If you ever think womp womp about something, that means write a paper. And there are lots of papers written about this. All right. The mean and the covariance matrix, this is where we have to use the scale identification method. But instead of having one latent variable where it to set its mean and standard deviation, now we have multiple. Okay? The same identification constraints apply. Number one, well, I'm getting ahead of myself. Before we get to scale identification, we need to know that we have enough items per latent variable to measure it. Bayes, it turns out, through the magic of priors, will let you estimate quite a few things, but they may be empirically unidentified, meaning you don't get the estimates aren't actually from data, they're from your prior more than anything else. So remember before I said we need 3 items per dimension to estimate it. That's generally true. It is possible to estimate a model where you have 3 observed variables for one dimension, and if that dimension is correlated with another one, 2 latent variables for the other. But let's just stay with 3 or more. Besides, that's not usually a good scenario. If you're trying to give people scores, 3 items are going to be very unreliable. But there are other uses for it, structural considerations. Like what is the structure of latent traits? How correlated are they, and so forth. Um, the scale identification is the problem here, though, right? We need to know what the mean is and the variance is for each latent variable. There are 2 methods to this. One we'll use today, one we'll use next week. Standardized factors is what we use today. We're going to set the diagonal elements of sigma theta, the covariance matrix of the factors, to 1. Right? That's saying that the variance of each dimension is 1. That's similar to saying, that's exactly saying the standard deviation for each dimension is 1. Right? We're going to set the mean vector to 0 for all latent variables. And then we're going to estimate all of the unique correlations in sigma. So what we're going to result with this is a factor correlation matrix. We sometimes call that phi. All right? The other method of identification, which we'll cover more next week, is something we call marker item parameters. Right? So if we want to estimate a factor variance, we have to fix one of the loading or slope parameters to 1 for one latent variable per dimension. Right? So that means we have 2 factors. We can take the first item's loading and set it to 1, and that identifies the variance for dimension 2. Here, let's go back to our Q matrix. So if we set the loading for the first item to 1, we could estimate the variance of the non-governmental factor. And for the second item, if we set the variance of its loading to 1, we can estimate the loading to 1, we can estimate the variance of the governmental factor. Right? Similarly, we can do the same thing for factor means. We can set item intercepts to 1 item to 0, or to 1, fix it to a value for each dimension that you can estimate, each latent variable you have. Okay, questions on any of this so far? So today, standardized factors. Next week, marker items. Cool? All right. This is more on the scale identification. We mentioned that before. Let's keep moving. The observed item model is our graded response model. So remember from last week, this is my graded response model modified slide. I made a mistake on this slide also, but fixed it, right? This is the same model procedure. The only difference is in the submodel's linear predictor, right? Inside of the exponent in the inverse logit transform, we now have the potential to have more than one different latent trait. Right? If you can just remember from a few slides ago, I walked through the math behind this ugly monstrosity. All that did was select the appropriate loading times its factor to show up on that model line. So our model itself, the categorical nature of the data, remember a categorical observed variable is one where there's multiple categories possible, that stays the same, right? The data side, in this case, stays the same. The theory side, the right-hand side, has changed, and we have more than one latent variable there. Any questions on that? All right. Is the seatbelt still fastened? Are you still buckled in? Because Stan gets a little weird here. There's an additional estimation problem that we have to talk about. Okay, so we knew in Stan, first of all, that Stan uses thresholds instead of intercepts. That's no problem. We know how to fix that, right? It just changes the ordering of our thresholds. No big deal, right? That's not our problem. Here's the model block, though. This is where the problem comes. All right, let's go into our model. First, I always start with our item. Our item response follows ordered logistic. That's our graded response model. Remember, in ordered logistic, there were two parts, two arguments. The first was everything but the threshold. So now, that's what this is. Theta matrix times lambda matrix is what I built on my matrix slide right here. Our theta matrix is every possible latent variable a person has. Our lambda matrix is which lambdas are zero versus which lambdas are estimated. And so when we put the two together as a matrix product, if there's a zero in our lambda matrix, it makes that theta not apply to that item's submodel in the graded response. So this theta matrix is a matrix type in data, and I'll show that on the next slide. And our lambda matrix is, again, another matrix type, but this has zeros. It's not quite a Q matrix. Right? It's like a Q matrix superimposed over all the lambdas, right? Where the Q matrix values are zero, lambda matrix values are zero. But where the Q matrix values are one, the lambda matrix values are the parameter we're estimating. Does that make sense? Yeah? Okay. Now, the lambda matrix has to be transposed to make the math work. Theta matrix is person by dimension. So it's number of persons by two dimensions. In this case, lambda matrix is items by dimensions. So the transpose of that makes dimensions by items. Right? So that should make it work. Finally, the threshold for each item shows up here. This is the same as it was in graded response land. Right? Each threshold shows up. We model the thresholds with a multivariate normal distribution where we have a mean vector with the hyperparameters for each item and the covariance matrix with the hyperparameters for each item. If you remember the covariance matrix, that's a three-dimensional array we had to talk about last time, whereas the mean vector is a two-dimensional array. Remember all that? Okay. Now we got to get a little bit crazy. Actually, no. Let me back up. Lambda is the same as last time too, right? But I want to talk a little bit about the difference between lambda and lambda matrix. Lambda, what I've defined here, is all the numeric values of all of my loadings in one vector. So lambda is not lambda matrix. Lambda is all of these loadings put into one vector without regard for which pattern they need to be. When I do that to simplify my Stan code, because now I can just say each one of those follows a multivariate normal distribution with a mean vector and covariance matrix for them. Okay? So I will show in a couple slides how I go from lambda, which is all the parameters, to lambda matrix, which is like a pattern matrix of which parameters are zero versus being estimated. I'll show you that in just a bit. Okay? Okay. Now let's talk theta. Theta's prior distribution is multivariate normal. Turns out multi-normal Cholesky is what we have here. Cholesky. A Cholesky decomposition is a factorization of the covariance matrix. Wow, that's a lot of words. Decomposition, factorization, it's a mess. So let's describe a little bit more of that. There we go. So theta itself is an array of latent variables, right? And we put those latent variables into this theta matrix later on as well. What we end up doing then is taking the correlation matrix of the thetas. I called it covariance before, but we know this is correlation because the diagonal is all one. And we define for it a prior vector, a prior distribution using something called the LKJ prior. LKJ prior stands for Lewandowski. Oh boy, what's the K? Where'd it go? Lewandowski, Kurowicka, and Joe, 2009, came up with the prior for correlation matrices. 2009 was a great year for me, although I didn't realize it at the time. Because up to 2009, I was struggling with this. But this paper made a big difference in my life, a big difference in the world of people trying to do Bayesian psychometrics, and it's amazing. Um, I'll talk a little bit more about this now. Let's talk about what a Cholesky decomposition is. Turns out, let's take a look if I can make an example here. Nope. All right. Let's make a matrix, shall we? The correlation matrix is, let's make a 2 by 2 correlation matrix. This is a simple diagonal matrix, but let's make this, oh, nope. Here we go. Here's a simple correlation matrix, right? So if we have a matrix that's positive definite and symmetric, which the correlation matrix should be, we can convert this matrix into a pair of diagonal or triangular matrices. So let me just show you what happens here. Turns out there's a Cholesky function in R, and it creates the following matrix, right? So what the heck is going on here? That's the upper triangle. So that would be, I need the transpose. Hang on just a second here. No, I don't want to type to Siri. No, Siri, don't talk either. And now Siri is, oh, I'm just going to lose my mind again. I should just have a class on what Jonathan says to technology that makes him mad. But let's talk about this. The Cholesky makes triangular matrix such that the transpose of that matrix times just that matrix returns the correlation matrix. All right, so what does that mean? That means all the information in our correlation matrix is saved in this triangular matrix right here. All right, how are we doing with that? That's cool. But why do we do it? Well, it turns out to take, let's see if I can see it here. I'm going to go out of order in my slides, but this will help. Uh, Basically, the idea is this. The problem we have is to take the inverse or the determinant of our correlation matrix. Um, there's a lot of calculation needed, right? So if we're going to talk about, if we're showing you the steps of how to find the matrix inverse, let's see. Mathisfun.com. All right. Here are this. There's a 2 by 2 matrix. Let's see here. Okay, so for a 2 by 2 matrix, you can see what's going to happen here. A 2 by 2 matrix, if we want its inverse, it's this: 1 over A times D minus B times C of each of these elements of those times this matrix. All right, let's see if I have a 3 by 3 on here. I want to show you what happens when you get bigger matrices. Uh, there are all sorts of ways, but this is it. Look at all these calculations you need for a matrix inverse. It's a lot. And I did see one before. This is fun. Math is fun. Look, it's Comic Sans font, right? Isn't that? No, maybe not. Maybe it's not Comic Sans. Anyway, it should be. It should be Comic Sans. There's an alternative way that we can use. This called a Gauss-Jordan method, which basically tries to, well, there's a lot of calculations too. Let's do this. Matrix inverse diagonal. Let's show what matrix inverse in the Cholesky is. So the big picture is the matrix inverse under a Cholesky makes it easier to invert because if you think of this matrix here, I'll just talk. If you think of this matrix, this Cholesky right here, and I'm going to print out the lower triangle. Pivot, impact. No, no, no. So this is the lower triangular matrix right here. All right. If you think of this as a system of equations, right, where you're trying to say, 1 times x, or better yet, if this is a series of coefficients in a linear equation, right, 1 times x plus 0 times y equals some number, you can quickly figure out what that number needs to be. You remember the series of equations? X plus y equals 10, x minus y equals 2, something like that, and you had to go solve for x and solve for y. Well, it turns out if the first equation only was x equals, that makes that system super easy, right? If x plus y equals 10, let's try this. Here. Yeah, never mind. X plus y equals 10, our first equation would just be x equals 10, right? And then with x equals 10, we can go to our second equation, which is 0.5x plus 0.86y equals some number, I don't know, 2, right? So we'd have 5 plus 0.86 times y equals 2, which we can quickly solve for y. So what's happening in a matrix, finding the inverse of a matrix, can be greatly simplified by using back substitution or forward substitution, depending on which triangular of the Cholesky, if you have a diagonal matrix involved. So what that means is, in the computer, every time that you do a product, every time that you multiply numbers or divide numbers together, heck, add, subtract, every operation you do, there's numerical precision error, right? Floating point numbers aren't always expressed correctly, and every operation may degrade the number itself. So turns out the Cholesky decomposition, using it to find a matrix determinant or a matrix inverse, greatly reduces the number of calculations needed, thereby making the result more accurate. How are we doing? Seatbelt still fastened? Okay. How many of you have done Cholesky work before in like linear models? Have you seen them before? Cool. There are a ton of decompositions. If you look at the LM function in R to run a linear model, it runs off of something called the QR decomposition. And this is the closest we come to really, really cool. Do you ever heard of the computer scientist Alan Turing before? Historic, famous British scientist, World War II, cracked the Enigma code, right? Totally smart dude. QR comes from him. Pretty cool, right? So there you go. Our connection to World War II. There we are. But that being said, so what we can do in Stan to make numerical precision work better is to use this multinormal Cholesky. And so what that's doing is taking our mean vector of thetas, our hyperparameters for the means, which we're going to set to 0 today, and it's going to take the lower triangular Cholesky of the correlation matrix. Weird, but this is sort of the result that's stored. And because we're having to estimate those correlations, we do need to define a prior on the correlation matrix to ensure that it is positive definite, right? And ensure that the correlations stay in bounds, -1 to 1. Well, it turns out the LKJ prior does just that. There's a function for LJK core Cholesky in Stan. The hyperparameter for it in this case, is eta, called eta. When eta is 1, it's like saying your density is uniform over all correlations. So it's the empirical prior that is diffuse or uninformative. So when you see my code on the previous slide where I actually hard-coded 1.0, that was to make a point, I like to make this empirical prior be uninformative, right? If theta is, if the hyperparameter is bigger than 1, then it sort of forces the correlations towards 0. So more of the mass is towards 0. And if it's between 0 and 1, then that density sort of moves away from 0. So you're pushing the correlation toward the edges. So you can see the hyperparameter itself works pretty well, is pretty nice, and LJK makes it so we can estimate a correlation. All right, still seatbelts buckled? Let's talk about, here's the math. Who wants to do the matrix math? Let's do it. Why not? For those of you who don't do matrices, just sit back and try to pretend like you're learning, like you're immersed in a language you've never heard before. All right. So if we take it turns out the determinant of the correlation matrix, we need that to calculate the likelihood, is equal to the determinant of the lower triangular of Cholesky times upper triangular of Cholesky, right? That's this thing right here. Because R is equal to L times L transpose, right? From the previous slide, you see R is L times L transpose. We just substitute R there. Well, it turns out there are some algebra we can do in the determinant. The determinant of a product of matrices is equal to the product of determinants of matrices. In this case, here. And it turns out the determinant of a triangular matrix and the determinant of its transpose are equal. So this is effectively saying like this is the determinant squared. And even more fun is that the determinant of a triangular matrix is simply the product of the diagonal elements right here. So if you look at this triangular matrix, it's a squared product, excuse me. We would expect the determinant of this correlation matrix I have up here to be 1 times 0.866 squared. Let's see if I can do that. Let's see how close this is. Pretty close, right? There's the rounding error I was mentioning to you. The determinant of the correlation matrix, right about 0.75. Had I carried all the precision of this right here, I bet I could do this. There it is. There's all the numbers, right? So the determinant becomes super easy. It's a product of the diagonal. That's easy to calculate, so we can do that. For the inverse, it works a little bit differently. We have to actually consider the pre and post multiplying matrices. And again, we take this correlation matrix and replace it with its determinant. It's Cholesky. And then what we end up with is if we can actually, the inverse of a product of matrices is really the product of the inverse of the matrices. So we can sort of reorient those. And it turns out this side right here is this side transpose. So we could solve this side through back substitution, the process I just described to you with the system of linear equation. And we return it to our likelihood times negative 1/2 that we had up in front here. So it moves much quicker. Any questions on any of this? It's complicated, right? I want you to understand a little bit of it. The reality of it is, if you just understand to use multinomial Cholesky right here and LJK core Cholesky, that's a good first step. Just know a little bit why that's there, okay? All right, so we talk parameters real quick. We have a couple minutes left. First, the ordered thresholds are the same from last time. Our vector of loadings is the same from last time. However, this time we have to define how many loadings we have. Remember, it's not one per item necessarily. It's the sum of the numbers of ones in the Q matrix. So we're going to figure that out as we go later on. Now, here's the fun part. Theta, we know we have two thetas. We have to build that as an array object too. It's an array of vectors. And so we have people in the first element, and we have the number of factors we have in the second element. So that's like saying theta is a number of persons by two matrix. Good with all that? Maybe. Maybe not, but hang in there. Watch this again. Play around with it a little bit. The Cholesky factor core statement is a special data type in Stan for our last part, the theta correlation matrix. That's the low, and I have the L at the end to denote this is the lower triangle of the Cholesky. This theta core L, if we declare it as a Cholesky factor core type in Stan, we just need to tell it how many factors we have, how many dimensions it has. And Stan will reserve this to be a correlation matrix Cholesky factorization, which is awesome. We don't have to do the work of making the Cholesky. It'll do it for us. Okay? Cool. All right. Now, then the transform data block is where everything starts to go nuts again, too. So, what I'm going to have you do when we get to next time, I'm going to quickly show this real quick. We're on the data block, we're going to import the Q matrix. But there's this transform data block in Stan, which I don't think I've talked about prior to this point. Transform data is where we take our input data from Stan and we do things to it that we can use in the model statement. And here, what we're going to do is take our Q matrix and figure out how many loadings we're estimating and figuring out the pattern of those loadings. So which ones should be zero, which ones should be not zero in our lambda, in this case, what did I call it? Lambda matrix right here. So what transform data is going to do for us is basically investigate our Q matrix that we submit, figure out how many loadings there are and what the pattern of loadings happens to be. And I'll talk more about how that process works when we get to next week. No, Thursday. Gosh, I'm going crazy. Any questions on any of this? All right. Well, that's it for me today. Starting on this slide on Thursday and create and bring the seatbelt. You'll need it. All right. All right. I'm going to stop for today. Thank you for your time and patience. And